everyone. Welcome back to Learning at 11th Hour. Today I'm going to discuss about the ABCD parameters, also called as the transmission line parameters in two-port networks. Let's go into the video. The ABCD parameters are going to basically represent the relationship between the input and the output quantities in this two-port network. So if we have a linear passive network with two ports, one of the ports is going to act as the input. So the current is going to be driven in, I'm going to call it as I1 due to the voltage V1. And since this is an input output kind of a relationship, here normally we would have drawn the current in this manner and called it as I2. But here we are going to consider that this is going to come out of the output terminal. And therefore, this is minus I2 because the green arrow shows the direction of I2. And since here we consider port 2 to be the output port, we consider I2 as coming out of port 2 and therefore minus I2. And this voltage is going to be V2. Now, the ABCD parameters or the transmission parameter matrix can be written in this manner. So, this is going to be basically a a voltage current pair kind of a relationship. So, we'll have uh, the V1 I1, the input voltage and input current, the parameters A, B, C, and D, and we'll have the output voltage and output current. So when we frame the equations, what we really get here is V1 is equal to AV2 minus BI2 and I1 is equal to CV2 minus DI2. So we can now obtain the transmission parameters in this manner. So we can have A. So to find A, we can consider I2 to be 0 and then A would become V1 by V2 provided I2 is equal to 0. So if I2 is going to be 0, it means that port 2 is going to be open circuited. So this parameter is actually called as open circuit parameter, and this is a ratio between the voltages where the numerator is the input voltage and the denominator is the output voltage. So usually when we have a ratio between the output voltage over the input voltage, that parameter is called as the gain. But since this is just reverse of it, this is called as reverse voltage gain. Reverse voltage gain. So that is A. Next, we can compute B. And to find out B, we can consider that V2 is equal to 0 and then B would become V1 by I2 and this minus sign would be retained provided V2 is equal to 0. So if V2 is equal to 0, it means that this is going to be a short circuit parameter and V by I is nothing but an impedance parameter. But look at the subscripts. The numerator voltage is 1 and the denominator's current is 2. So this is basically a transfer parameter across the input and the output. So we can call this as short circuit because V2 is 0, transfer impedance, right? Then we can obtain the parameter C. And to do that, we again consider I2 is 0 and C would then become I1 by V2. So this is again a transfer parameter where we are having I2 equal to 0, which means this is an open circuit parameter. But look at this, the ratio is current by voltage, which means this is a transfer admittance. So we can write this out as open circuit transfer admittance. It's the reciprocal of resistance or impedance, right? Next, we can obtain the parameter D. And again, to do that, we consider V2 is 0. So we get D as minus of I1 by I2, provided V2 is 0. So if V2 has to be 0, this becomes a short circuit parameter. And if you notice, this is a ratio between the input and the output current. So this is a gain, a current gain, but not really the direct current gain. This is a reverse current gain parameter because we have the input current in the numerator and the output in the denominator. So this parameter becomes short circuit reverse current gain. So these parameters are actually called as transmission line parameters. That's because in transmission lines, or transmission parameters rather, because in transmission lines, the currents are going to enter uh, one end and they are going to leave at the other end. And we need to establish a relationship between the sending end and the receiving end, which is done with the help of these transmission parameters. So the reason why they are called as transmission parameters is because the entire network here is made to represent that of a transmission line. We can now obtain the relationship between the ABCD parameters, the Z parameters, as well as the Y parameters. So there are several derivations that would go into it, but that can be found in any standard books and you can go through that. So I'll just write out the relationship between the ABCD parameters, the Z parameters, and the Y parameters out here. So let's write out the relationships between the Z parameters, the Y parameters, and the ABCD parameters. So the Z parameter is basically these. This is the Z matrix or the impedance matrix. Then we have the Y parameters. So they are again Y21 and Y22. And the transmission parameters is simply A, B, C, and D. Now, if I want to write out the Z parameters in terms of ABCD parameters, so this is what it would be. A by C would be Z11, delta T by C would be Z12, 1 by C would be Z21, and D by C would be Z22, where delta T is going to be AD minus BC. We can write out the Y parameters in terms of the transmission parameters in this manner. So Y11 would be D by B, Y12 is minus delta T by B, Y21 is minus 1 by B, and Y22 would be A by B. And here again, delta T is going to be AD minus BC. We can write the ABCD parameters in terms of the Z and Y parameters also. So in terms of the Z parameters, it would be Z11 by Z21 is going to be A. Delta Z by Z21 will be B. 1 by Z21 is C. And Z22 by Z21 will be D. Here, delta Z will be given as Z11 Z22 minus Z12 into Z21. We can also write the ABCD parameters in terms of Y. So that is minus Y22 by Y21 will be A, minus 1 by Y21 will be B, minus delta Y by Y21 will be C, and minus Y11 by Y21 will be D. Here again, we can express delta y as y11 y22 minus y21 into y12. So these are the relationships that exist between the z parameters, the y parameters, and the transmission or ABCD parameters. Let us now look at the condition that needs to be satisfied by the two port network in terms of ABCD parameters, so as to say that two port network is reciprocal or the two port network is symmetrical. So here, let's obtain the condition for reciprocity in terms of the transmission parameters. We have to write out the ABCD parameters for these two conditions. So for circuit A, what is the equation, and for circuit B, what is the equation, right? So looking at this circuit, we see that V2 is 0, and this I2 is actually minus I2 dash. So I2 is minus I2 dash, looking at this configuration. So we can replace V2 with 0, and what we get here is V1, which is nothing but Vs, that is the uh, forced voltage or the voltage source which we've connected to port 1. So Vs is equal to A into 0 minus B times of minus of I2 dash. So we get Vs is equal to B I2 dash. So therefore, I2 dash by Vs is equal to 1 by B. This is one condition that we've obtained. Now let's try and obtain the second condition from the configuration B. So here we see that V2 is going to be Vs, and V1 is 0. So when I apply it to this equation, V1 is equal to A V2 minus B I2, and I1 is equal to CV2 minus DI2. So when I apply these over here, I'll get the ratio. I should get the ratio I1 dash by Vs, so to say. And the condition for reciprocity is that I2 dash by Vs should be the same as I1 dash by Vs, meaning that if I am going to excite either one of the ports with the current I, then the open circuit voltage measured across that particular port is going to be V. So therefore, be it at port 2 or port 1, I by V, that ratio should be consistent because it's across the same network. So if I'm able to equate I2 dash by Vs and I1 dash by Vs, I'll get my condition for reciprocity. So let me try and find this ratio. So to do that, let me first replace V2 with Vs and make V1 as 0. So I'll get 0 is equal to A into Vs minus B into I2. And in the equation over here, I1 actually becomes minus I1 dash is equal to C times of Vs minus D times of I2. From this equation, we can compute I2. So we know AVs is equal to B times I2. Therefore, I2 is going to be equal to A into Vs by B. So if I'm able to replace this I2 over here, I would get minus I1 dash is CVs minus D into A Vs by B. So let me take LCM, and what I get here is minus I1 dash is C into B minus D into A, the whole into Vs. And our objective was to find out I1 dash by Vs. This is what we need to find. So we've almost arrived there. If I could just bring this Vs down. So I1 dash by Vs is equal to, I can adjust this minus sign over here, saying AD minus BC by B. So in order to say that the circuit is reciprocal, I just need to say I2 dash by Vs is I1 dash by Vs. So for the same kind of excitation on either ports, I'm going to be injecting the same amount of current, which means I can say 1 by B is equal to AD minus BC by B, cancelling out the denominators in both the cases. My condition for reciprocity, therefore, becomes AD minus BC is equal to 1. So that's all with today's video. I hope you've understood the concept of transmission parameters through this video and how it is related to the Z and the Y parameters, and also the condition for reciprocity in terms of transmission parameters. In the upcoming videos, we'll discuss some numericals related to it. Please do subscribe to this channel to watch more such videos. Thanks a lot for watching.